Plane curves and parametric equations. If f and g are functions defined on some interval I, then the set of points f of t, g of t is what we call a plane curve. The equations x equals f of t, y equals g of t are called parametric equations, and t is called the parameter. So basically what we have is a set of points in the plane, as you can see here, and these points are determined by two independent functions, f of t and g of t. And so for a particular value of t, x will be equal to f of that value of t, and y is equal to g of that value of t. And together we get the point xy, where x and y are defined in this way. Now this is going to give you a set of points in the plane, just like any other equation involving y and x will give you. However, it gives you more information because as t increases, you move along this curve in a specific direction. So a plane curve is not just simply a graph of points. It is a set of points that make up a graph, but then there's also an orientation to how you move through that set of points. As an example, let's sketch the curve defined by the parametric equations x equals t squared minus 3t and y equals t minus 1. So to graph, at first, we're just going to select a bunch of values of t, as you can see here in the table. So for each of these values of t, we will plug it into each equation to determine x and y. So for example, when t equals negative 2, we plug that in here, and we get x is equal to negative 2 quantity squared minus 3 times negative 2, and this is 4 plus 6, which is equal to 10. And then we plug it into the other equation, y equals negative 2 minus 1, which is negative 3. And that gives us the point 10, negative 3, which is this point right here. So that's the first point. When you plug in more values of t, you will get more points. And you can see all these points on the graph here. And next to each one of the points, we write down which value of t gave us that point. Because if we don't do this, the parameter t is invisible in this graph. Notice that there is not a t-axis. There's only an x-axis and a y-axis. So you don't have to list the values of t next to your graph, but in this case, as a first example, it's nice to see how we got those. So what we have here is a set of points that clearly makes a parabola, but there is an orientation to this parabola. It's not simply a set of points. For a specific value of t, as t increases, we move in this direction through that parabola. Another thing I want to show you is that we could have gotten the same set of points as in the last example by using a different parameterization. Now, I won't go through all the details here, but if you were to graph this set of parametric equations, notice that you get the same parabola that we got previously, but notice that the orientation is completely different, right? So now as t increases, it is moving in this direction through that parabola. Here's yet another parameterization that gives you the same set of points as the previous one did, and it moves in the same direction, but it moves twice as fast. Notice that there are very few t values here that take us through the same set of points that we got in the first example. So a set of points can have many different parameterizations, but those parameterizations will be all a little bit different in terms of where they start, which direction they travel, and how fast they travel. When given a set of parametric equations, we can also eliminate the parameter in those equations. So here's the parametric equations that we had in example 1. What I want to do here is eliminate the parameter. So this means I want to get an equation just with x and y, no t. Notice that we can solve for t in the second equation here. We can say t is equal to y plus 1. And then we can take y plus 1 and we can plug it in for t in the first equation. If we do that, x is going to become y plus 1 squared minus 3 times y plus 1. And then if we multiply things out here, we get y squared plus 2y plus 1 minus 3y minus 3. And finally, x is going to be y squared minus y minus 2. So this is the rectangular equation that corresponds to these parametric equations that you see here. And of course, we know that if you graph this, this is going to be a parabola. But when we graph this as a set of points, we lose all notion of orientation or speed, right? This is just a set of points. Parametric equations are really good at modeling circular motion. The following parametric equations model the position of a moving object at time t. X equals cosine of t, y equals sine of t, where t is some positive number. So because we know that cosine squared of t plus sine squared of t is always equal to 1, and if x is going to be cosine of t, then cosine squared would just be x squared, and if y is sine of t, sine squared would be y squared, you can see quite easily that this means x squared plus y squared equals 1 is the rectangular equation that describes these parametric equations. And we know that this is a unit circle. Now, we also know that this is going to be a unit circle because these are the definitions of the trigonometric functions sine and cosine on the unit circle. So in either case here, if t is greater than or equal to 0, we are going to get the unit circle being traced out in this direction because t is just representing the angle through which we have rotated here. So these parametric equations basically describe circular motion, where t is the angle through which we have rotated, and x and y are just the points on the unit circle that correspond to that angle. Now, what about the parametric equations x equals sine of t and y equals 2 minus cosine squared of t? We can do a little playing around with the equation here, and we can say y is equal to 2 minus, and then cosine squared is 1 minus sine squared. And then we can simplify further. This is going to be 2 minus 1 plus sine squared, which is equal to 1 plus sine squared. So we have y equals 1 plus sine squared, and then we know that x is sine of t. So we can replace sine of t with x here, and we get y is equal to 1 plus x squared, or more commonly, we would simply write this as y equals x squared plus 1. Now, we know the graph of y equals x squared plus 1 is a parabola that looks like this, right? But the graph of the parametric equations does not look like this. Look at the graph over here. So what we have is just a very small piece of this graph. Now, why did that happen? Well, if you think about it, remember, sine of t is always a number between -1 and +1. And so if x equals sine of t, this means that x can only be a number between -1 and +1. So down here on this graph of this parabola, we're only going to get the section of the graph that corresponds to those x values, right? So I'm going to erase the other part of the graph. It's just not possible, because if x is sine of t, x can never be a number bigger than 1 or less than -1. Also, we know that cosine of t is in between 1 and -1. Therefore, cosine squared of t is always going to be in between 0 and 1, right? Because when you square it, you won't get a negative. And so if y is 2 minus cosine squared, This means that y is going to be 2 minus a number between 0 and 1. Well, 2 minus 0 is 2, and 2 minus 1 is 1. So that means that y has to be a number in between 1 and 2. And you can see that right here on the graph. Indeed, for this section of the graph, y is a number between 1 and 2. So what ultimately happens here, if you let t equal 0, for example, you get x equals 0, that's this point. If you let t equal another angle, it's going to start to move in this direction, but it's going to get to this point and it's going to turn around and start moving back in the other direction. And so as t increases, the movement on this curve just oscillates back and forth. And this is really interesting, and one of the reasons why parametric equations are so useful is because without them, we really can't describe this kind of motion easily using rectangular equations. In our final example, we're going to find parametric equations for a graph. And here we want to find the parametric equations for the line of slope 3 that passes through the point 2, 6. Now, there are many different parameterizations, but one thing we could do is we could just find the rectangular equation. And so we know that y minus y1 is equal to the slope times x minus x1. And if it passes through the point 2, 6, that means x1 would be 2 and y1 would be 6. And if the slope is 3, then m, of course, would be 3. And that would give us y minus 6 equals 3 times x minus 2. And this is y minus 6 equals 3x minus 6, or simply y equals 3x. Now, that's the rectangular equation. What about parametric equations? Well, what we can do is simply let x be equal to t, and this would cover all real numbers t, and then y would just be 3 times t, right? Because y is 3x. And so this is one possible parameterization for the line that you see here. And that concludes this video lesson.